In previous class, we have discussed about the bearing capacity of soil and some basic definitions we have discussed. So in today's class, we are going to discuss about the bearing capacity of shallow foundations. And here I'm going to discuss about the failure pattern of foundations. Okay. So here I given the most carefully designed structures can fail if they are not supported by a suitable foundations. Even though you have taken utmost care for the superstructure, and if you have not taken care about the foundation, and if you have not supported that foundation in a suitable strata, the structure may fail like this. Okay, so the bearing capacity of soil is very important to understand as well as for the design purpose. So here again we'll discuss some of the basic definition, even though we have discussed in the previous class. So we'll again discuss some of the basic definitions once again. So here the shallow foundations are also called as a spread foundations. The screen is visible, right?
Yes, sir.
Right. Here the shallow foundations are also called as a spread foundations. But how shallow is shallow here? So what is the definition of shallow foundation? So the common definition of shallow foundations refers to the case where the founding depth or the foundation depth is less than the breadth. If this foundation depth D is less than the width of the foundation, then that we call as a shallow foundation. So that is when depth is less than the width of the foundation, then the foundation is called as a shallow foundations. But what about wide raft foundations here? So the above definition is not acceptable for the wide rafts, but here therefore a foundation is shallow if the depth is less than 3 meters or less than the breadth of the foundation is called as shallow foundations. Okay. Then coming to the shallow foundation, the types here, these also were discussed in the previous class. So here the pad foundations, or you can call it as a isolated foundation footings like this, the first one. So these are usually provided to support the structural columns. They may be a circular, square or rectangular slab sections. They are called as a pad foundations. And the strip foundations, and this is also called the shallow foundation. The strip foundations has a length, here this length is greater than, very much greater than the breadth. They are normally provided for the load bearing walls or closely spaced columns where it is not economical to deal with the individual pads. So these are called as a strip foundations. Then coming to the raft or mat foundations. So here the raft foundations are required on a soils of low bearing capacity or where the structural columns are very closely spaced in both the directions such that the individual pads would not nearly touch each other. So in that situation, the mat foundation will be using. Then coming to the foundation design criteria. So what are the criteria to be followed for the design of foundation? So there are three main design criteria must be considered for the design of the shallow foundation. So they are, it should be adequate depth, means the founding depth or the foundation depth, that is the depth from the surface to its underside, should be sufficient to prevent the effects due to changes of the ground surface. So it should be adequate depth. Then second one is sufficient depth to prevent overturning moment when the structure is subjected to horizontal forces. Horizontal forces could be because of wind forces or even because of the seismic forces. It should be sufficient to take care of the overturning moments. So the depth should be sufficient. Then second criteria is limiting the settlement. So it should not settle more. Okay. So the amount of tolerable total as well as differential settlements depends on the functional and user requirement and also the economic factors. Then the next is the most settlement damage may be classified as architectural damage as they normally affect the finishes. Means whenever a structure gets settles down, first its appearance get damaged. Hence, they are classified as a architectural damages, as they are normally affects the finishes. Then coming to the again the third factor. So very important, this third factor. So before designing the foundation of a shallow, this third factor is plays a very important role. So factor of safety against a shear failure. So most of the structures, whenever they fail in foundation, they fail by shear failure. Like this, you can look at the picture here. So it has tilted sideward. So it is because of the shear failure. So next I am going to discuss about the different types of shear failures generally occurred in foundations. So in a foundations, so what will happen? The shear failure occurs when the soil divides into a separate zones, which is moved partially or fully along the slip surface. So look at this picture. You all can see this picture, right? So this one.
Yes, sir.
1 minute. Okay, this one. This picture you all can see.
Yes, sir.
So this is the failure surface of the foundation under shear. So look at this one. This is one shear plane up to here, and another shear plane is this one. Okay. Suppose if the building tilts rightward, so if it tilts like this, okay. So this side shear failure you will get like this. If it fails, or if tilts leftward, you'll get this type of failure plane. Okay, so here in a foundations, a shear failure occurs when the soil divides into separate zones which move partially or fully along the slip surfaces. These are the slip surfaces. Okay, these are the slip surfaces. Along this surface, the structure get tilted and it moves along the slip surfaces. But while slipping, so this is the soil is being divided into three separate zones. So zone 1, zone 2, zone 3. So that is passive zone, active zone, and radial zone. There are different types of zone will come along according to the Tarzagi's foundation failure theory. And at this point, a plastic yielding condition has developed whereby the shear stresses along the slip surface has reached a limiting value, that is ultimate limit state will be reaching. Then finally the foundation will get fail, means completely the soil is get converted into a plastic state. Then once it reaches the plastic state, and further if the load get increases, it won't be taking, then the final stage will be what? The failure stage. That is what we call the ultimate. When it reaches the ultimate state, the foundation get fails. That's why at this point, means at ultimate point, when it reaches the ultimate state, a plastic yielding condition has developed whereby the shear stresses along the slip surface has reached the limiting value. The final stage will be the what? The failure stage, like this. So how the building has got tilted, so the ultimately the building will get collapsed due to shear failure. So here the principal criteria for the design will be what? Satisfying the given factor of safety against the shear failure. Means whatever the factor of safety you take for the design, it should get satisfied with that factor of safety. That is the principal criteria for design of the foundation. Then what are the modes of shear failures? Generally a foundation will fail. So depending on the stiffness of foundation soil and depth of foundation, the following are the modes of shear failures experienced by the foundation soil. So these three modes of failure, the general shear failure, local shear failure, and punching shear failure. So these three modes are very important for you for the examination point of view. And generally the foundation will fail in shear, but in shear also there are three modes. They are general shear failure, local shear failure, and punching shear failures. So what are these general, local, and punching? We'll discuss one by one. So you can see the picture here, how the foundation will fail in general shear, how it will fail in local shear and also the punching shear. And corresponding to this failure, load versus settlement graph is also plotted here for the general shear, local shear, as well as the punching shear. So let us discuss about one by one how and when this general shear will occur and which type of soil generally this general shear will occur. Similarly, local shear, which soil, again the punching shear failure in which soil, we'll discuss it one by one. So consider there are, as I discussed, the three modes of failures. So out of that, the first one I am taking here is general shear failure. This picture is visible to you, all right? You can able to read, all of you?
Yes, sir. Yes, sir.
Okay. Try to understand how the general shear failure will take place here. This mode of failure, general shear failure, so which generally occurs in a dense or over consolidated soil. Just remember, it occurs in a dense or over consolidated soil, or you can call it as a very stiff soil. You can call it as a stiff soil. It occurs generally in a stiff soil or a dense soil, or it is called as a over consolidated soil of low compressibility. Very important, low compressibility. And here what will happen, whenever a footing is been subjecting to a loading like this, when the footing is subjecting to loading here, you can look at this picture here, a footing is subjecting to the load Q. So what will happen at the time of failure here, at the time of failure, most of the soil within the stress zone, so this is completely the stress zone under the footing, this part is completely under stress. Okay, so most of the soil within the stress zone which will reach the plastic state, except the central portion. This remaining part will be reaching the plastic state. Means what will happen here, a clearly defined plastic yield slip forms under the footing and develops outwards to the surface. Okay, so try to understand this general shear failure here. What will happen in case of this general shear failure? What will happen? A continuous failure surface develops. See, look here, the continuous shear, that is a shear failure, will be developing between the edges of the footing as well as the ground surface. And when this pressure, means the load which is acting per unit area of the footing, so the load per unit area we call as a pressure, when this pressure approaches the ultimate bearing capacity, then what will happen, the state of plastic equilibrium is reached and initially and in the soil around the edges of the footing. And then what happens, it gradually spreads downward, and also outwards. So what will happen, ultimately the state of plastic equilibrium is fully developed. Once it fully developed throughout the soil, then then what will happen, the failure surface will be occurring above the soil. And this failure is accompanied by appearance of the failure surfaces by considering bulging also. Here the bulging will be taking place. Also the soil mass gets sheared. And finally what will happen, the slip movement would occur only on one side, which is accompanied by the tilting of the footing like this. The tilting of the footing will take place finally like this. So what are the characteristics of this type of a failure? So what will happen here? So clearly defined plastic yield slip forms first, then what will happen, under the footing and develop outwards to the surface, that failure plane will develop. And here what will happen, a heaving of the ground occurs on both sides of the footing. Means heaving means the failure surface will reach up to the ground surface, and above the ground surface the heaving will take place, it like this. And this is what is the bulging, and this is heaving. So bulging as well as heaving will take place. So as I said, at the time of failure of foundation, what will happen, tilting will take place like this. It's a tilting, then heaving will take place, and as well as bulging will be takes place for the foundations. Okay, so bulging will occur at the side of the foundations. Then, so we can say failure plane is a fully developed. Here the failure plane is fully developed, and this failure will be sudden or a catastrophic without giving any warning. This type of failure will be takes place, means the failure is sudden without prior warning here. And also the bulging on the ground surface adjacent to the foundation will be visible. You can see here a bulging will be takes place over the surface which is adjacent to the footing, and generally it occurs in a relatively strong soils, or you can call it as a dense sand, or you can call it as a steep soil. And here, as I said, the ultimate bearing capacity is well defined. So you can easily define where the failure is being taking place in this case of failure. So you can see the graph here, the load versus settlement graph. As the load is go on increasing, the settlement is also go on increasing. So it will increases as the load increases, the settlement is also increasing. Settlement is also increasing. So at one point of time, what will happen when it reaches the ultimate here, QU, when it reaches ultimate bearing capacity of the soil? So what will happen? The failure will be sudden and catastrophic. Suddenly it settles down like this. Okay, so the load is increasing, the settlement is also increasing, but here the what will happen? The failure pattern can be well defined, easily defined here. Okay, so the ultimate bearing capacity is well defined. So QU can be easily calculated from this graph here. This will be the QU, the ultimate load has reached here, and after this one, the failure will be sudden or catastrophic failure. Without giving any prior warning, the foundation will get fail. So this type of failure is called as general shear failure. So general shear failure, how it takes place? Usually this mode of failure occurs in a dense, remember, dense or over consolidated soils of low compressibility, or you can call it a stiff soil. Generally this type of failure will be occurring. So here what will happen? A clearly defined plastic yield zone will be forming here. As the load is go on increasing, the stresses will start begin in the soil, but the except the center portion of the soil, the other portions of the soil will be reaching the plastic state. So once they reach the plastic state, the failure surface will start forming. And how the failure surface will be forming here? They are be forming during failure. They tilt, the foundation may get tilt like this, either the leftward or the rightward. Because of the tilting, what will happen? The bulging of the plane, the soil starts bulging, that is a failure plane. It will bulge, as well as the heaving will take place above the ground surface like this. The heave will be takes place, so it will reach up to the ground surface. Here it will take the heaving because of what? Because of the tilt. Okay, then we can say it is heaving of the ground occurs on both sides of the footings. So look here, it is a heaving, and this is called as a heave, okay, as well as bulging. Okay, then here the failure is sudden and often accompanied by a severe tilting on one side of the footing. Okay, so this is a failure pattern of general shear failure. And one more thing you have to remember, it's very important, is here the ultimate bearing capacity is well defined. We can easily identify where the failure is being taking place, so that can be easily identified in this case. Okay, so here you can easily mark here. So this is ultimate bearing capacity. At this point the foundation fails, so means once it reaches the ultimate capacity of the soil, if you increase the further load, it will be takes sudden failure, that is a catastrophic failure. Without giving any prior warning, it will fails. And here the well defined failure surface reaching up to the ground surface. So these are the some characteristics of the general shear failure. So in this general shear failure, you can observe the tilting of the footing. Okay, so once it started tilting because of the soil has reached the plastic state, the heaving, bulging, all will takes place because of the tilt. Either it may tilt leftward or the rightward. So any way it may tilt, but the failure surface will be forming over the ground surface adjacent to the footing, and these surfaces called as a heaving surfaces as well as the bulging surfaces. So like this, so the soil will fail. Once the soil fails, means the entire foundation may get failed. Okay, and it will occurs in a dense or over consolidated soil, or you can call it as a stiff soil. So this is the graph for the load versus settlement curve. As the load increases, the settlement gets increases, and at one point of time, it will reach the ultimate. Then once it reaches the ultimate, the further increment of the load will lead to the catastrophic failure, or you can call it as a sudden failure. And here the ultimate that is ultimate capacity can be, bearing capacity can be easily defined here. So you can easily identify here the ultimate bearing capacity of the soil. So these are the some characteristics of the general shear failure. And coming to the next one, the local shear failure. So this is the this type of failure we call as a local shear failure. This local shear failure is an intermediate failure mode, which is characterized by well-defined slip surfaces below the footing. Again, you can characterize well-defined slip surfaces like this. Well-defined slip surfaces below the footing and extending only a short depth into the soil mass. So these will be extending into a short depth, and these surfaces will not be reaching the ground surface. So like a previous case, how they have reached the ground surface, they are extended larger depth below the ground soil mass, and in this local shear failure, these failure surfaces will not be extending much below the soil mass, as well as they will not reach the ground surface also. Even though if they are reaching, they are very negligible plane you may get in this case. This is called a local shear failure. So what will happen in which case, which type of soil it will occur? It will occur in a compressible soils. So it will occur in a compressible soils, or you can call it as a loose sand. It occurs in a loose sand or soft clay. So this type of soils, this failure will takes place. That is a local shear failure. Occurs in a compressible soil. So these two kinds of soils can be easily compressible. So in this type of soils, this type of failure will occur. That is a local shear failure. And here a significant vertical movement may takes place before any noticeable heaving. Means before failure, before showing any heaving on the surface, so it will move vertically down before showing any noticeable heaving. And here the shear planes develop but fail to extend the ground surface. Means the shear planes will be developing here also, but they will not reach the ground surface. The shear planes will not reach the ground surface here. And here what will happen, a very little tilting may take place. So in previous case, there was a large tilting, hence you were getting there the bulging as well as the heaving. But in this case, the tilting is very little, hence this shear planes will not reach the ground surface, even though they are reaching, but they are of negligible surface. And here the settlement which occurs usually is the principal design criteria. Means whatever the settlement is taking place here, so it is the main design criteria to be considered here. Hence the characteristics are what? The failure plane is not completely defined here. So like previous, the failure plane is not completely defined. So in previous case, we were easily identified the failure plane, at what point it was failing, that was the ultimate bearing capacity, and later after that it was failing suddenly. But in this case, the failure plane is not defined properly here. Okay, so you can say the failure is a progressive here. So whether here failure, it has failed here or it has failed here, we cannot identify it properly in case of a local shear fail. So, and again, sudden jerks at the failure. So here the sudden jerks will take place because it is moving vertically in vertical direction. So here significant vertical movement may takes place because the jerking will also takes place here and before any noticeable heaving. Okay, so because of this, what happens? So here a sudden jerks at the failure will be takes place. Again, what will happen? The small amount of bulging might be observed. So here a small amount of bulging might be observed. Okay, in this case, occurs in a sand or a clay with a medium compaction. And this is what we call as a local shear failure. Plot graph load versus settlement. You can take the load per unit area. That is what we call get a pressure. When you plot load versus settlement, so this is the graph we get the gradual failure like this. It will fails, but what will happen here? The failure pattern will is not defined clearly. We cannot define it clearly. Here in this case, like a previous, and failure surfaces don't reach the ground surface also here. And there is only a slight bulging of the soil around the footing will take place. You can observe here a slight bulging can be observed around the footing here. And failure is defined by a large settlement. Here the failure is defined by very large settlement. Settlement will take place very much large. And failure is not sudden like a previous. And there is no tilting of footing. Even though it is tilted, it is very little. Like previous, it will not tilt much, and a large settlement can be observed here. So, and the failure pattern is not defined well, and ultimate bearing capacities are not defined well like previous. So we have calculated ultimate bearing capacity QU in this case, but in this case, so it is a progressive collapse. So we cannot easily identify where it is failing because the failure is progressive. So because of this, we cannot identify the ultimate bearing capacity, or you can say it is ultimate bearing capacity is not well defined. So this local shear failure is intermediate failure mode, which is characterized by the well-defined slip surface, like this well-defined slip surface below the footing, and which is extending only a short distance into the soil mass. So this is what we call as a local shear failure. Okay. So next is the punching shear failure. So the punching shear failure means the foundation which is sinks into the soil like a punch. It is called as a punching shear failure. And in which kind of soil it occurs? It occurs in a weak compressible soils. So you can see here, whenever the load is being applying per unit area, the foundation sinks into the soil like a punch. Hence it is called as a punching shear failure. And it will occur in a weak compressible soils, compressible soils like a loose sand or a soft clays. It will occur. And here what will happen? A considerable vertical movement will take place. The footing will be moving vertically down, and slip surface is restricted to the vertical plane adjacent to the sides of the footing. Means you may not get any slip surfaces like a previous cases, but it is moving vertically down. It is it is sinking into the foundation soil, and you may not get any failure surfaces like a previous like this. So the slip surfaces are restricted to vertical planes. Only it is failing in a vertical plane, which is adjacent to the sides of the footing. And here heaving at the surface is usually absent. Means you may not get any heaving like this, like a previous case, how it was forming in previous cases and all. You may not get the heaving failure here. The heaving at the surface is usually absent and may be replaced by what? The drag down. Means this footing is going down vertically. It is punching into the foundation soil, or it is sinking into the soil like a punch. Hence it may not form any heaving over the surfaces like this. Normally there will not be any tilting here. So normally there will be no tilting like a previous case, because as it is punching the soil, it will go vertically down. This type of failure what we call as a punching shear failure. And this kind of failure may be observed in a highly compressible clays. Remember, highly compressible clays or in a loose sands. So this type of failure will take place. That is, punching shear failure will be taking place. So again, whenever you plot the load versus settlement graph like this, the load per unit area, when you plot, then you will get the pressure. So load per unit area is a pressure versus a settlement. So you will get the graph again. So again, you cannot easily identify where the failure load is. So the failure surface will not be defined properly here. So here the no failure pattern is observed properly here, like a previous how we have identified in case of a general shear failure and all. So in punching shear failure, because it is failing in vertical direction, so the failure pattern cannot be observed properly here, and failure surface is vertical or slightly inclined. Sometimes it is most of the case it is a vertical only, but slightly inclined will be observed in this case. And here the no bulging of soil around the footing can be observed, no bulging at all here, and there is no tilting of footing like a previous, as I said. And very large settlement you will get here, very large settlement, and bearing capacity of the soil or the bearing capacity is not well defined because of what? The progressive collapse of the soil or progressive collapse of the foundation. The bearing capacity of the soil is not defined well like previous. So it's very important, note it down. So many a times this question has appeared in exam. So explain 3 modes of failure of foundation soil. What are they? General shear failure, local shear failure, and punching shear failure. So 3 modes. So you write point by point how these will occur and which kind of soil these failure will be occurring, and also plot the load versus settlement graph to explain the failure pattern of these kinds of failure of foundation. Okay. So any doubt here in these 3 modes? General shear failure,
No,
local, all of you understood? So in the first case, how it fails, just to remember, it fails by large tilting, heaving will be forming here, and large bulging will take place. And here a well-defined failure plane will be observed here, and you can say ultimate bearing capacity can be easily identified, and after reaching the ultimate bearing capacity, it will be as the failure pattern is a catastrophic or the sudden. In next case, the failure surface may not be reaching the surfaces, that is ground surfaces, even though it is bulging on sideward, but it may not be reaching the ground surface, or it is very little, and the tilting may be a very small. And whenever you plot the load versus settlement, it is a progressive collapse here. You will get punching, which will be moving vertically down. There is no tilting at all here. There is no bulging. There is no heaving. So it will be punching, or it is sinks into the foundation soil. Again, the failure pattern is how it is progressive. Okay. The large settlement will be occurring in these 2 cases. Large settlement you may observe here, and bearing capacity is not well defined. Hence, it is called as a progressive failure. I hope you understood all 3 types. So coming to the again important definitions with respect to those failures. Again, I can define. I already defined these 3 terms. That is a foundation pressure, that is a gross loading intensity, as well as a net bearing pressure. The previous class I explained about this by taking the numerical. I explained what is the gross pressure or what is the net pressure. Once again, you just listen. The gross loading intensity means is the intensity of total pressure on the ground beneath the foundation after the structure has been erected and fully loaded. That is called as a gross loading. It includes what? It includes the self weight of the soil, that is overburden pressure, that is gamma into D, and also it includes what? The self weight of the footing, as well as it includes what? The live load acting on the column. So that is what we call the gross intensity, gross loading intensity. Then the net bearing pressure is what? Or the net foundation pressure is what? is the net change in the total stress experienced by the soil at the base of the foundation. So here if you take sigma as a stress removed due to excavation, that is gamma into D. If you remove it, then whatever the pressure the footing experiences at the that is beneath the footing, that is what we call as a net bearing pressure. That where Q is the total foundation pressure or the contact pressure at the base of the foundation, then the net will be what? Q minus sigma. That gives you the net. So that is net pressure is due to only the column load. What do we get? Then again, the net effective bearing pressure or the net effective foundation pressure, how you get here? The net foundation pressure expressed in terms of effective stress, that is due to the overburden pressure. When the water table is above the base of the foundation, then the net effective bearing pressure is given by. Suppose if you come across any water table above the base of the foundation, how it can be taken? The net pressure will be what? The total pressure which includes the overburden pressure Q, that is column pressure, the overburden pressure, or the self weight of the floating. So you have to deduct the water pressure. How much it is? This much height of the water is there. Then HW into gamma W. Gamma W is what? The specific weight of water multiplied by the height of water present. If you deduct it, you will get the net effective bearing pressure in case of water table if you come across above the foundation. So try to understand here. This is the net bearing capacity, the total pressure minus the pressure due to that is overburden as well as pressure due to water pressure. Then this graph we have plotted in 3 modes of failure, the load versus settlement curve. Whenever the load per unit area go on increasing, the settlement of the soil will take place in this direction. As the load increases, the settlement will be taking place. The settlement will be taking place at one point of time. It will reach the maximum. That is what we call the ultimate load. And this ultimate load we take for the design purpose. In a foundation design, we take this one by plotting the load versus settlement curve. A foundation is being subjecting to the load per unit area, then you have to plot the graph load versus settlement, then you have to calculate the ultimate load carrying capacity of the foundation soil. Then the ultimate bearing capacity is what? Is the value of the loading intensity at which the supporting ground fails in shear. Till the failure of foundation in shear, you have to go on applying the load and finally you have to reach the, or you have to get the ultimate bearing capacity of the soil. Is the value of the loading intensity at which the supporting ground fails in a shear, that is called ultimate bearing capacity. Then the net means the net ultimate bearing capacity is the value of net loading intensity at which the supporting ground fails in a shear. It is a net, means excluding overburden pressure. So that is called net ultimate bearing capacity. QNF and QF. QF is the ultimate bearing capacity. NF is the net ultimate bearing capacity. Again, as the same, the factor of safety to be taken into account. The factor of safety against a shear failure, which is defined as the ratio between the net ultimate bearing capacity and the net bearing pressure. The ratio between the net ultimate bearing capacity and the net bearing pressures are called as a factor of safety for the foundation. Generally, for a building foundations, the recommended factor of safety is between 3 and 2.5. Okay, this is to be taken. This is the recommended. And presumed bearing pressure is what? Is the net loading intensity considered appropriate to the particular type of the ground for a preliminary design purpose. For a preliminary design purpose, some of the bearing pressure to be assumed, that is called as a presumed bearing pressure. So is the net loading intensity considered appropriate to the particular type of ground for a preliminary design purposes, and the value is based on the local experience or by calculation from the strength test using the factor of safety against the shear failure. So this is what we call as a presumed bearing pressure. So again, the allowable bearing pressures, you can define allowable bearing pressure also. So this also where we calculate in foundation design is the maximum allowable net loading intensity of the ground in a given case, taking into consideration the bearing capacity and the estimated amount and the rate of settlement that will occur that what we call as allowable bearing pressure. The considering the shear failure, allowable design bearing capacity is given by. So this is the formula to use allowable bearing capacity. And here in this case, sigma is what? The effective surcharge at the base level of the foundation. This is effective surcharge at the base level of the foundation, which is to be taken. So QA is the allowable bearing pressure, QF is the ultimate bearing capacity minus the effective surcharge at the base level divided by the factor of safety, again plus the effective surcharge at the base level to be taken as the allowable bearing pressure. So with this next class, I am going to discuss about the Terzaghi's bearing capacity formula. On this formula, you will be having many numericals to be solved, but the base for to understand the Terzaghi's bearing capacity formula, if you want to understand the Terzaghi's bearing capacity formula for the shallow foundations, the base is what? The base is what? This is the failure pattern is the base. So if you understand in clearly how these three types of failure pattern, how these occurs and what are these and which kind of soils these will occur, if you understand these three pattern, you can easily understand the Terzaghi's failure pattern or the Terzaghi's bearing capacity formula. There are some assumption to be made before deriving the Terzaghi's bearing capacity formula. So that we'll discuss in the next class, and also some of the numericals also. I hope you understood the today's class. The important here is the modes of failure is important. The modes of failure is very, very important. If you understood that one, then the rest all you can easily.
Bearing capacity is the load which a soil can support without failure. Geotechnical engineers use their understanding of bearing capacity to design systems to safely transfer the load from structures to underlying soils. The loading produces compressive and shear forces in these soils. If the load is large enough, the shear forces induced in the soil will become higher than the shear strength of the soil. This results in failure. There are three types of bearing capacity failures that can occur. One type of failure is punching shear. This happens in loose sands, in thin layers of strong soils underlaid by weak soils, and in weak clays which are loaded slowly. Failure develops gradually in this setting due to the high compressibility of these soils. Little to no soil disturbance is seen at the surface when punching shear occurs, but structures experience high levels of settlement. Local shear failure occurs in cohesionless and loose to medium dense soils. This failure mode has a well-defined shear surface directly under the footing that may or may not be seen at the surface of the soil. Local shear failure happens gradually as the footing continues to experience settlement and movement along the shear plane. General shear failure occurs in dense cohesionless soils and undrained cohesive soils. General shear failure is characterized by a well-defined shear plane with clearly formed disturbances in the surface soils. This type of failure occurs suddenly and can cause significant rotation of the structure. Over the years, there have been several extreme instances of bearing capacity failure. One historic event involved the Transcona grain elevator constructed in Manitoba, Canada. The elevator design had overestimated the bearing capacity of the soil and underestimated the load from the grain. This led to the structure experiencing a sudden and dramatic general shear failure. Engineers have developed methods to safely support structures and transfer loads in soils with low or insufficient bearing capacities. One method is to distribute the load of the structure over a larger surface area. Mat and raft foundations are used for this application and usually span the entire footprint of the structure they support. Another option is to bypass weak soil layers and transfer loads to stronger layers or even bedrock below. This is accomplished with deep foundations. There are several types of deep foundations which are generally categorized as driven piles, drilled shafts, and auger piles. Soil improvement can also be used with shallow foundations to get the necessary strength for structural support. Soil improvement technologies strengthen and reinforce existing soil structures at sites to increase bearing capacity. There are many different options for soil improvement, with new technologies being developed regularly.